All right. So one thing happened during the break that I wanted to show all of you because it worked out. I was doing this on the fly. I was worried about this move AL stuff. So I made another program called test bits here. Oops, I didn't want GCC. I wanted to just nano test bits. There it is. Okay. So all I did was put all ones in EAX and then do this move AL1 and then do an interrupt break. This will do a break that stops the programming. So I compiled that and loaded it. And then when I run it in GDB, and all I have to do is just run it, it will crash as it hits a seg fault. And if I do info registers, you'll see that the result is the first 3 bytes still contain FF, and the only thing that got the 1 was the right 8 bits. So when they tell you that the correct assembly language for shellcode to put 1 in EAX is move AL EAX, I object. It should be XOR EAX or EAX to fill it with zeros, and then move AL1. But this is an important issue I was just talking to the class about. Shellcode is sloppy. It makes assumptions. So in practice, it's probably good enough to just do this move. Let me get back to this one here, there. In practice, it's probably good enough to just do this move AL1 because A usually contains 0. And a lot of shellcode makes assumptions like that. And when you actually use it, it won't be right on your system. So be aware, you're using something that's not even up to like a beta test version. You're using something that's minimized down to the smallest possible attack that will usually work under whatever conditions the author thought it would work. And if you don't satisfy those conditions, you may be sorry. Anyway, so I want to just demonstrate a couple projects here that are good, clean fun. Let me close a bunch of these extra windows. Okay, so I'm going to go right back to my home page to make sure everybody knows how to get here. You start at samsclass.info, and then you go to 127 and projects. And I want to show you project 3 and project 10x. So we'll start with project 3. And this is the simplest attack with real shellcode. So I'm going to just shove this over to the right and execute it in this thing here. So I'm going to get out of my debugger. And let's take a look at ASLR. So I'm going to turn on ASLR, address space layout randomization. This is the defense which messes up most of these attacks. So with that defense on, I've got a file called ESP, which I got from your textbook authors. This, you can print registers from inside C with this ASM command. So I can now create an assembly variable, which will then print the value of ESP. So I can compile that. I've already compiled it. So if I run ESP, it prints out the value of the stack pointer. If I run it again, it's different every time. 420, 440, and so on. That's what address space layout randomization is supposed to do. Every time you load a code, it goes randomly in different places in memory. And therefore, when you try to inject code and jump to it, you can't find it. And this is one of the main defenses that meant simple stack overflows quit working. So we're going to turn it off. That's the value that turns it on. If you just put a 0 in that same location, that turns it off. And now if I just run this code, it's the same every time. So that's the way I want to leave my machine for our simple attack here. And this is the same thing as using a version of Linux that's 10 years old. Or for that matter, a version of Windows before Vista, before they had this defense. Okay, so that's the joy of getting rid of ASLR. Now we're going to create a vulnerable program. I got bo1.c. This program has a main routine that calls something called copier and then prints done. And all copier does is take input variable and put it in a buffer that's only 100 characters big. And that came from argv1, which was in the command line. So I give the name of the program and then some text, and that text will be passed into this function and copied into something that's only 100 characters big. When you compile it, you have to use a few switches. I'm not sure you need all these switches, but it works. These are some switches to tell it to compile without any of the modern defenses. It's probably be enough to just use static and no pi. But anyway, this combination of switches does work. Notice you get a bunch of warnings, which is okay, but you don't get errors. Errors means it wouldn't work. So now I can run my bo1 on A, and it just prints done. But if I give it a long string, longer than 100, it will run past. That one wasn't long enough, so I'm going to double that one. There, that's pretty long. Now it crashes. So at some point, I filled things up to where I hit something important like the EIP. So now I want to see if I've got it. So I GDB it to see what I've got here, bo1. And now I run it. And I put in that, oops, I got to run it with that junk, pardon me. It crashes all alone because I didn't run anything I ought to run with this junk here. There we go. I'm going to start it again. Okay, this was not long enough, so it terminated normally. It gave me a done. So now I'm going to run it with 2 of those, which I think is more than it can handle. And now it crashes. And when it crashes, the extended instruction pointer contains 41, 41, 41, 41, which means that some of these A's ended up in the EIP. So now I'm ready to go to town. I'm ready to do it. So now I'm going to run it again. And I'm going to put in the first one of these. And now I'm going to put in B, B, C, C, D, D, E, E, F, F, G, G, H, something like that. And see if some of that will hit the EIP. Start from the beginning. And it wasn't enough, okay? So I need something longer than that. So I'm going to put that in the clipboard, run that, and then I'll just keep going, NNO. That might be long enough. And it is long enough. I hit it with 51, 51, 52, 52. Now, I want an ASCII table. There are many ways to do it. I'm just a wimp. I use the internet. There's command line commands to do it. I forget what 51 and 52 are. In hex, 51 is Q and R. Okay, so that is my attack string. And wherever I had Q and R is what's going to end up in EIP. So I'm going to copy that much of it, run it again with that. And now I'm going to put in 1, 2, 3, 4, my favorite test. So if I did it right, that will end up in the EIP. So I say yes, and again, 1, 2, 3, 4, it worked. And you can check it with info registers, and you'll see the EIP is now 1, 2, 3, 4, because 31 is 1, 32 is 2, and so on. So now I control the EIP. Now, that's the first step. I now found a simple overflow exploit, and I can control the EIP. So now, if I can do that, I've done all that. I'd like to view, let's view the registers at this point. Might as well do that. Let's disassemble main. And that's main, which calls the function called copier. And the buffer overflow is actually in the function called copier. So I'm going to quit from here and disassemble copier. Okay, here's copier. So as usual, like I say, be like someone only looks at the pictures, start over here. Here's string copy with some details I don't care about. This is the function that copies the string into something that's going to be too small. So this is where the overflow happens. Here's where it tries to return and crashes. So I'm going to put a breakpoint here. Now, I've already put the right amount of code in my clipboard, and I don't want to copy anything else till I'm done with that. So let me put it here. There. That's my exploit with the 1, 2, 3, 4. I just didn't want to lose that. Now that I've got it, now I can break here. I'm going to copy that and put a break there, break star there. Now I'm going to run with this stuff, my 1, 2, 3, 4, run with that and restart, and it should hit the breakpoint. And if I info registers, at this point, EIP is not damaged yet because it hasn't tried to return. But it has hurt the stored return value on the stack, so I want to look at the stack. So I see the stack ends at 5B8, so I'm going to X, 40X, EIP, and, oh, not ESP, pardon me, there we are. Okay, and make my window a little bigger. Okay, and my EBP is 5B8. So I go to the 5B, this is 5B0, 5B4, this is 5B8. So that is the stack frame. This is what I always do before thinking much. IR, examine ESP, that's the stack frame. Here's all the A's I put in. Then here come these other characters like B and C and D, and here's the 1, 2, 3, 4. So now I can inject a value here and go anywhere I want. So I just have to figure out where to go. And since I'm going to have to put arbitrary hexadecimal values in here, I want to start using Python. So let's put this exploit in Python before going any further. So I'm going to do nano DE1, demo 1, just so I don't get too confused. Okay, let's put in shebang, user, bin, env Python, and then attack string equals that. Okay, except I don't want the 1, 2, 3, 4. I'm going to put that in separately. I'm going to call that EIP equals, I'm going to start with 1, 2, 3, 4, and later on that's going to be something else. So then it's print attack plus EIP. That's my plan. That should do it. That should put the right amount of junk on the screen to have the effect. So I'm going to run chmod plus X, that script, and then run it. That prints it on the screen, so now I'm going to put it in a file, I'll call it dattack1 without a .py. I'm going to call it da1, I'm trying to keep it short. Okay, so that's my attack string. And now if I run my attack, I can do GDB. See, I can run this thing as bo1 on A, and that works. If I want to feed in the contents of a file, I can do it this way. That should do it. That will cause the segmentation fault. This is one of the many ways to take the contents of a file and feed it into a program. And the advantage of this one is it will fit nicely into GDB. So it's GDB bo./bo1, and I'm going to use that in a minute. And I'm going to make this quiet so it doesn't scroll up the screen so much. Now I'm going to run with args like that. I think that'll do it. Let's see what happens. It exited normally, so I followed it up. Let me check my slides. I always have a little trouble with this stuff. Oh, not the slides, but the instructions. All right. Okay, run $cat e2. Thought that's what I did. Oh, I don't need the minus arg. Okay, we'll just do it this way. There, let's see what that does. There, that works. I hit the seg fault and I put the 1, 2, 3, 4. So now I can do that. Okay, now we've gotten this far to this magic spot where you can see that I control the EIP and I control 100 bytes of code before the EIP. So I can put executable code here and I can jump to it. So now I have to make shellcode. You can make shellcode with MSF Venom, but here I'm just using shellcode I found online. There's shellcode that spawns a dash shell. Somebody published it. It's just assembly code. That'll work. So now I want to use a NOP sled as well. So this is my final exploit, which I called B3, and I think it's in this directory. Let me bring it up. Quit from here, nano B3. Okay, so what this does, it puts in enough A's. It turns out 112 A's is what you need. Here's the 1, 2, 3, 4 that's going to end up in the EIP. Now I make a NOP sled, which is 64 times 90. 90 is the NOP binary, executable. And this is the shellcode. And the way I wrote it here, I don't have to keep track of how long the shellcode is, so I can try different shellcode. It's going to, oh, this time I did put it in hard code here. But normally what I would do, I'm just going to improve my code. I've learned to not do it this way. Length of NOP sled minus length of shellcode. There. That's a good plan. Now, if I use different shellcode, it'll automatically expand as long as the shellcode is small enough to fit in the available space. So now, this is going to hopefully put 1, 2, 3, 4 in the EIP, and it's going to put a NOP sled and shellcode up among the A's. So let's see if this works. This is B3. So let's run B3 and put it in E3. Okay, and now let's do GDB of BO1. and run with $cat E3. Good. It ended with a 1, 2, 3, 4. That's what I wanted. So now I want to look at my stack. So I'm going to disassemble copier, right? And find the address after the overflow, which is here, and put a break there. So now I'll catch it before it crashes. Now I'm going to run it again here, starting from the beginning. It doesn't crash. It hits the breakpoint. So you always do info registers first. And now you see ESP is here and EB is 5B8. So I look at the stack and I'm looking for 5B8, which is here. So now that's the stack frame. Here's the EIP containing my 1, 2, 3, 4. Here's what I injected. NOP sled, a bunch of 90s. Then this junk here, C389, all that junk is the shellcode that I got from the internet. Then after the shellcode comes some more A's, 4141, which I'll never use. They're just to pad it to get down here. So I want to put in this address the NOP sled. As long as I can jump back to any of those 90s, it will do NOP egg and execute my egg, which is my shellcode. So I could choose any address back here, although you have to choose an address that doesn't contain a 0, or nothing will work because you can't eject anything past a 0. So right now, this looks pretty good up here, BFFF 560. That's someplace in an NOP sled. So let's put that in for the instruction pointer. So I quit. I go copy. Let's see, I have, what was I called the last one? I called it B3. Let's copy B3 to B4, nano B4. By the way, don't keep editing the same file or you'll be sorry, because you very often make mistakes and then you wish you had the previous one that still worked. So that's why I make a whole chain of them, even up to like 9 or 10 of them. I change a little bit, make the next one, the next one, the next one. Especially when you're first developing exploits, I make plenty of mistakes and go off on the wrong track. And then I wish I could go back to the one that did something. So this is what I want to put in instead of that for EIP. So I put in this junk backwards, 60, F5, FF, BF. That's the, I can get rid of the colors, might look better on the video. So that should do it. That should inject the code and jump to it. Let's see if it works. I run B4 and put it in E4. Then I GDB this thing and I run with $cat E4. And it worked. It executed dash and ran dash here. So that is my shellcode working. And let's see how it worked. Let's exit from dash and disassemble copier. Oops, that's the wrong thing. It's disassemble copier. Okay, I gotta start over again. Let's just quit and reload it. Okay. Here, now disassemble copier. Okay, here's where it does the, am I losing my mind? Why am I not seeing, BO1 is the wrong program, huh? Is this BO1? Wait a minute now. All right, I've fallen off my track. It is BO1, and the name of the function is really called copier. So something has gone wrong. Okay, GDB BO1, disassemble, copier. And why am I not supposed, what is this nonsense? All right, I'm losing my mind. Let's run BO1. Wait, BO1 is now crashing, or BO1 on A, that runs, okay, so it's working. All right, let's go back to the previous one. That's a good idea. But I didn't run anything. All right, I'm losing my mind. You guys have been watching this. What did I do wrong? Up here, we disassembled copier and I saw reasonable stuff. So what did I do wrong? All right, there we are. That's what copier should have, this string copy thing in it. Did I recompile it or something? So how in the world is copier now different? I'm going to go mad. All right, let's just recompile it. My code to compile stop copier is up here. and somehow I wiped it out. So let's just do it again. See if we can get back to where things make sense here. That will compile it. That will run it. GDB, a BO1 will run it. If I disassemble copier, it is still doing this to me. This makes no sense at all. It's jumping to some address that doesn't work. I have somehow totally fouled things up. So I'm going to make a directory, demo 3, and get rid of everything else and recompile that function to get back to a clean condition. And if not that, I'll restart my machine. Somehow I've fallen off the track. Somebody, I imagine, will enjoy pointing out to me what I've done wrong. I don't understand how I could do this if I wanted to. Suddenly the disassembly isn't working. But anyway, now if I compile it here, that should give me the stuff I need. And now if I do GDB of ./BO1 and then disassemble, copier, it still gives me this crazy thing here that makes no sense. Let's try, well, all right. Let's restart the machine, quit, reboot, and see if that does any good. Other than that, I'm just going to have to point to the instructions. If this happens to you, I won't know what to tell you. Somehow I seem to have destroyed GDB or something, and I've done this a lot of times, and I've never seen that happen before. Somehow when I disassemble it, I'm getting stupid answers. It's jumping to code that doesn't make any sense. So I've lost my thread, and we'll just go on to the next one if nothing gets better here. And maybe my virtual machine is dead too. It's waiting for me to log in. I don't know why, root. Oh, I probably have to restart SSH, which is service SSH start, I think. Okay. Service SSH start. Okay, now I should be able to get in. Okay, something's working. All right. CD 127, GDB./BO1, disassemble, copier. And we're still having this garbage where it's jumping ahead 1 byte, which makes no sense at all. One thing I wonder is if I compiled it without the static switch.
Are you running it from the right directory?
Yeah, this is the one I used earlier, 127. Yeah, and I even made another one. Let's try adding the plus static to it and see if that does any good. Other than that, I'm just going to go on to the next one because this one has stopped working and I cannot immediately figure out why. Now I want this. I'm going to put plus static in it, or dash static. And now I get an error. So I guess I can't do static. Let's try this. Static and no pi and none of this other junk. That might be good. Okay, let's try that. And now GDB, BO1. I may have to give it an argument. Disassemble, copier. Now I get a better answer. Now it is not calling an invalid. This is the copy, but it's no longer showing as a library call. I've seen this happen also before, where GDB stops telling you the name of the libraries, and I don't understand why it keeps happening. So there are some parts of this that baffle me. But anyway, I've got my exploit ready to go here. I just wanted to put a breakpoint here. Let's get out of here. And I think I called it E1 or something. I had my exploits. This is the one I just made. What is today? February 3rd, E4. Okay, so cat E4. Okay, and cat A4. How did I create E4? B4. B4. All right, fair enough. This is where I was trying to do this. I want to run E4, which came from B4. So the B4 is what creates my exploit. I put it in E4. And when I ran it, in GDB, B01, and then I run with cat E4, it works, and I get the dash shell. Now, doing this before somehow fouled up everything. We'll see what it does now. If I exit from this, and now I try to disassemble copier, I think that's not going to work because I have to restart the program. Let's quit, come back in, disassemble, copier, and good, it has not self-destructed. I don't know what happened before. Now I want to put a breakpoint here. It is doing the irritating thing of not telling me the name of the subroutines, but I'm used to that half the time in GDB. It fails to give you the name of the routines. I don't know why. Now I put a breakpoint there. Now I can watch what it does. So it's $cat E4. There we go. So now I have made it to the string copy routine, and you can see this is the string copy source routine, and GDB is being cruel by not telling me that here when it told me that earlier. That's an irritation, such is life. Now I can see the stack goes from 520 to 5A8, and I can examine it with 40X here. And here is 5A8. So let's look at what's going to happen here. It's going to put this value in the stack, which doesn't look good. I think I might have broke at the wrong point. All right. Where did I put my breakpoint? I put it at before the copy, 895. I put it before the call. So it hasn't done the copy yet. Good. So I need another breakpoint here. All right. So there. Now I have to continue to get the second breakpoint. And now if I examine the stack again, I'm going to get a different answer. 5A8 is here, and this is what I wanted to show you. Now I have put in this value, BFFF560, and that is this value, so it's going to jump up here, execute the NOPS, and run. So if I continue here, I now, it should work and execute the new program, bin dash. Then it complains about stuff I'm not going to worry about right now, because I want to show you a dirty trick, which is it worked inside the debugger, but it probably won't work outside the debugger. This is very common because the debugger is not perfect. It gets addresses wrong by up to like 50 or 60 in hexadecimal bytes. So if I feed in E4 out here, I get a seg fault instead of getting the desired result. And I have never found a solution for this. There is one solution which is really gruesome, which is to put a command inside the C code that prints out something like ESP, and then run it in the debugger and run it out of the debugger and see how wrong it is. People tell me this has to do with environment variables and stuff, but I've never seen anybody get it under control. I just do it the hard way. I use hex edit and do it by brute force. Here's the exploit that worked in the debugger. You make it, just move it around by 20, 40, 60, 80 bytes until it works. Last semester in Kali 2016.2, I had to subtract 50 from this number to make it work. Now I have to add 20 to this number to make it work in the latest version of Kali. So that 60 just goes to 80. I just move around trying to hit my NOP sled. If the NOP sled was big, like 500 bytes, I'd be fine. But it's only 64 bytes, and the debugger is off by more than that. So I've added 20 to it. Now if I run it, it still gives me a seg fault, so I got to just play with it. Add 20, add 40. Okay, I'm going to try adding 60, and then I'm going to try going the other way. Yep, all right. And so it was 60, I think, is where I started. Okay, now let's try 40. And try 20. Ha! So I had to subtract 40 from it this time. After restarting my machine, when I tried it earlier this morning, I had to add 20. Something is nuts. And if any of you figure it out, that would be swell. But anyway, I'm used to this. When you get it working in a debugger, you will have to adjust it by trial and error to make it work in the real operating system. Yeah. It depends on the code. If your NOP sled is really big, like 500 bytes, and you jump in the middle of it, then it won't happen. because the maximum amount of displacement seems to be about 80 bytes. And it doesn't always happen. So there are also, some people say there are ways to start the debugger that will decrease or eliminate this problem, but I've never found one reliable. Anyways, that's one part that causes great suffering by students doing the homework. Anyway, that took longer than I thought and kind of fell off the track. I think I'm not going to try to demonstrate 10x today because my demonstrations are collapsing under me, and I imagine it's because I got a cold that's making me stupider than usual. So rather than confuse you with demonstrations that don't work, I'll just say when you're done with that one, go on to this one, and let me point out the difference. This one here is from a guy taught a Black Hat class. You download this virtual machine, it's only 30 megs, and it runs a simple Linux that starts a web server listening here. The differences here are you're going to exploit the web server itself. So you're going to use HTTP GETs instead of just having a command line, and you're going to use return-oriented programming, so this works against a modern OS that has address-based layout randomization. So first you have to make code that will send to GETs. Now you were talking earlier about how to send a post up to the server, and this is how you do it in Python. It takes about 8 lines of code. This is a GET, but a post is the same. You connect to the socket with IP address and port number, then you just send text, GET, and this. This will send an A up to the server. It'll get a file called A. And that'll run, and then it'll give you a 200 OK, which, by the way, is the wrong answer. This is a fake web server that he wrote, which does not really obey the rules, because it shouldn't say OK unless it found a file called A. But this one will say OK unless it crashes. So anyway, it's a very simple imitation web server. So now you can fuzz it. You can send more A's. So I try sending 1,000 A's. And 1,000 A's cause it to crash, and you get no reply because the server crashes. Now this server is designed to make it easy, so not only does it always return to 200 until it crashes, it also automatically restarts after every crash to make life handy, which, by the way, is common for real servers. So now, and when it crashes, you can see on the panel that it's crashed at 41, 41, 41, 41. So this is a classic overflow of the same type. Some of those 1,000 A's ended up in the EIP. So you can now send up a variable number of A's by just using this code, which will take A and multiply it by N and ask the user for N. And you can just try different numbers. And what I found was 10, 50, 100, 150, 200, 170 did not crash, 180 did crash. That's about all you need. So 170 is harmless, 180 causes a crash. So now I put in 170, and then I just put in a string like this to see what part of it ends up in the EIP. And when it crashes with 43, 44, 44, 44, which is the C and the first 3 D's of this mess. So now I know exactly what to put in, which is 181 characters. And then the next 4 hit the EIP. So you're just reproducing the same process. Now it crashes with 42, 43, 44, 45, which is B, C, D, E. So you know how to hit the EIP. Now, the next thing which we have been skipping, which is irritating and necessary, is to track down the bad characters. We already talked in the lecture about how null is no good, but there are often other characters that the individual software regards as a terminator, which is just up to the developer. And in HTTP, it's things like spaces that separate fields. Space, tab, character, return, line feed, all these things are typically bad characters. So you have to test them. So I made something, since I have 170 characters here, I can put 128 to test them. So I put in the first 128 characters here and see what happens. And the result is it no longer crashes at this point, it says. Anyway, so I send that up, and it didn't work because the 0 stopped the attack. In fact, what happened is the 0 terminated the GET request, so it never even got the character return line feed to interpret it as a complete request. I got no answer at all. And from this end, I can't tell that, but if I look on the console of the server, it won't show me this crash, because it's still waiting for an attack. This is, in fact, the slow loris attack, where you send an incomplete request to a web server and it's waiting for the rest of it, because the 0 terminated it. So you have to try other ones, and you can guess what might be bad. 0 is null, you know that's bad. Tab is likely to be bad. line feed and carriage return are likely to be bad, space is likely to be bad. These are all things that are likely to terminate the field. So I made one, I started at 33, which is printable characters after the space. I imagine that all the characters from 33 to 127 are okay because those are normal ASCII characters. So I guessed they might be all right, and I put in those, and when I do that, it returns without crashing. There's no reply from the server, and it did crash up here. You can see it crashed with some of the letters there. So that means the exploit worked. It did put in enough characters. So this is how you confirm that the ones I guessed were good, from 33 through 127. And then I tested the high values, the high 128 here, from 128 to 256. And again, when you send them up, it has the same result. The program, all right. Again, anyway, that's the point. Now you have to go test them one by one. And I made one code someplace. Yeah, here's the one, testing one by one. So this one worked also. So I know that it's only the first 32 characters that might be trouble. And I just wrote a program that will test them one by one. So there, you can try to think of a smarter way to do it, but it took me maybe 30 or 40 tests to test all the bad characters. So it's an irritating thing I used to skip, but I got over it. Otherwise, your shellcode will never work because you don't know which characters to dodge. So once you have done this annoying task of finding out which characters are forbidden, you will have a list of bad characters. And in this case, there are 3 of them, 0, 10, and 13, which is null, carriage return, and line feed, which is kind of obvious, but you don't know. So now you have to make shellcode that will not have those characters. So I find the crash. Here I was able to put the BCDE. Now I have to find the code before the crash. I don't have the source code, and I don't even know the name of the module to disassemble, but you don't need it. This is another useful trick. You can run your debugging session. You can connect to the running process instead of launching it because it's already running on the server. You can connect with just --PID equals. That will connect to a running process, and now you can execute instructions. Next I will execute the next instruction without descending into subroutines. More precisely, it will descend into subroutines and return. This is called a step over in a disassembler. I stay at the same level and go to the next line of code wherever I am. And if you do that, that will start listening. And then you can you can now jump ahead by a number of instructions. I jumped ahead by 1, jump ahead by 10, jump ahead by 100. I can keep going until it crashes. So I had to do something like 700 jumps. I don't know where I am. I don't know the name of the routine. I don't have the source code, but I can still find out where it crashed. When it crashed, it tells me where I am. So I jump ahead by 100 instructions. I'm 73, 70, 90, all these. After this, when I did the next 100, it crashed. So somewhere within 100 instructions after this point is the crash. So now that I've done that, I can insert a breakpoint there and run it. And I can then jump ahead by 10s from there until it crashes. And I now get within 10 instructions of the crash. And then when I disassemble code there, I can figure out what happened. And here's what happened. It's done some kind of code up here, which somehow took that input and overran the buffer, and now it does a return. So this is a classic buffer overflow. I can guess it's going to crash when it tries to do this return. So I want to stop before it gets there. So I can put a break on this 7C location, on this leave instruction. That is a way to put a break after the overflow but before the crash, which is what I have to do to prepare the exploit. And I see a chat. Somebody may have a useful comment. Okay. Will your courses stay on YouTube forever? Yeah, well, that's my intention. Until Google changes their rules and takes them down, which God only knows, but I'm not planning to ever erase them voluntarily. Yeah, good. All right. Yeah, complete. That's what it is, complete. Complete with all the mistakes. But anyway, it is complete, which is how when I read the books like Gray Hat Hacking, they would tell you how to do it. And when I tried to do it, it didn't work because they didn't really tell you everything you needed to know. They assumed that you knew half of it already. And I try never to make that assumption. It helps to not know much myself. Anyway, so so now I can view it in the stack. Now I can see, here's the ASIN section, there's the BCDE, and now I can do it. So I have to find a useful address, And you can see I control these A's back here. So all I have to do is replace some of these A's with real shellcode and jump to it. So I find a useful address to put it. And here's the problem. I can't jump directly there. This is what's called return-oriented programming. And so if we did what I just did in the previous one, I would jump right to this address, like BFFF B910. And if I did that, it would only work if I didn't have address space layout randomization. But since I do, when I really run it, it's going to randomly relocate, so the address I feed in will be wrong. So the way you avoid that is you look for a value on the stack that points somewhere good. So look at the stack. This is the top of the stack. Here's one word into the stack, 2 words, 3 words into the stack. If I look at the 4th value, I get BFFF94C. And if I look here, BFFF94C is right there. So the stack happens to contain a pointer into the code I injected. This might seem like a stroke of luck, but in fact, it's very common, because the reason you overflowed the buffer is usually you just called some function that copied the contents of your input into some buffer that was too small. So it had a pointer to the code you put in. And it's a couple of words up the stack. So I have to, instead of trying to jump directly to this address, what I want to do is pop return. Pop will move the stack pointer over a word. Pop will move it over another word. Return will pop this and jump there. So if I can find pop return and jump to that code, it will execute this code, which I control. That's called a trampoline, and it's called return-oriented programming. I don't jump to instructions I inserted. I jump to instructions that are already there, and they jump to the code I inserted, and they find it for me wherever it is, because I refer to the stack that is loaded when it loads. So I don't need to know where the code is. I'm making my exploit portable. Now you have to find pop return, which in fact is a very common sequence of code. So info proc map will let you see the layout of the code. And you can view the assembly code in that region. This is where the text code is. And you can just start looking for pop return, but the first screen's not going to have it. And I tried like 10 or 20 screens and you don't see it. So I have to get a little smarter than that. What I did is turn on logging. If you turn on logging, everything that appears in GDB will go into a log file. Then I examined 2,000 instructions starting at this location and quit. And now I can view the log. And the log just has all that assembly code ready to go. Now you can use grep. Grep is the simple Linux command to look inside files. So I grep for return. How many returns are there? It turns out there's only 5 returns in there, and only 4 of them actually execute return. So I just look at them. You can do grep, and you can say -B4 to say, show me the line containing return, and show me 4 lines before it. So that single command does the whole job, because it shows here's a return and a bunch of adds, here's a return, but this one here is pop rat. So that code right there contains the code I need. And it's not in the stack that's getting relocated, it's in the main routine, which is always at 804. So this is the address I need. If I jump to that address, it will do pop return, find my code wherever it is on the stack, and jump to my code. That's return-oriented programming. This is what you must do in all modern operating systems. This is what overcomes address space layout randomization. So that's what I put there, 08, 04, 91, 02, that address. And that's the game. And now, here's another useful trick. When you're going to inject shellcode, it is very often the case that something is wrong with your shellcode. For example, it has a bad character that you failed to figure out, or something else is wrong with it. So before you put in real shellcode, put in CC. CC just makes a break. It's an executable instruction that stops the debugger, and you can tell that you did get there and execute stuff. Another thing, by the way, is you often do not have the permissions to execute the memory regions you're injecting into, and your shellcode won't run, and CC will detect that. So here is the exploit. I put in that value for the EIP, so it'll do pop ret, and where I'm going to have shellcode, I make this thing called dummy. That's just 80 bytes of CC. That's where I'm going to put shellcode later. but I'm attempting to execute that. So it's going to have a NOP sled, 20 bytes of 90, then CC. And if it works, it'll jump into my NOP sled and then execute the CC. And that's what you'll see. This is what it looks like in the stack. You have 90, 90, 90. You have the fake shellcode. Then you have a bunch of A's. Then way down at the end, you'll have that address. So if you run it, it will now do this. When you continue, it will now break, which is what you want. It stopped here at BFFF BBA5, and BBA5 is here, which is just what you expected. It jumped into the NOPs, executed the NOPs, and stopped at the first CC, which is actually here. But anyway, the first CC in that byte, that's what stopped it. So that proves I am able to find the injected code, and I'm able to execute code I put at that point. So now all I have to do is replace the CC with real shellcode. I could write it in assembler, but I'm not interested. I'm just going to use MSF Venom. MSF Venom will make shellcode any way you want. If you list the payloads, you'll see it can make it for anything, AIX and Android and any crazy thing. Here I want Linux, x86, and a bind, which is the simplest attack that will just open the listening port and take commands on it. And some of them are staged. It'll tell you over here. Yeah, staged. Staged commands are 2 stages. The first stage comes in, then it connects back to the server to download some more, and I don't want that. I want it all in one piece. So I choose a non-staged one. This is the simplest one, x86 shell bind TCP. That will open a port and listen, and when it gets commands on that port, it'll execute. And to see the options, you do -- payload options. In case you have to set any, there are some required options. Local port and our host, but it has a default value of 4444. So you don't need to specify it. It'll just listen on 4444, and I'm content with that for the moment. So all this is the entire command that generates our shellcode. I just tell it which one to generate. I accept the defaults, and I want it in the language Python. You can have it in any language you like, but my exploit is in Python, so why not save myself the bother? There it is. Now, this would be swell, except it's got a null byte in the middle of it, right? This is never going to work. That null byte is going to terminate the string. So you have to make it without bad characters, and that's in Metasploit. You specify the bad characters. And remember, there were 3. 0, 10, and 13 are the bad characters. So this will create shellcode without those. Now, this shellcode was 78 bytes long. But skipping those bad characters is going to require a sort of decoder in the front and make it a little bit longer. Now it's going to be 105 bytes long. But remember, I had more than that. I had something like 181 bytes to work with, so this will work. So now I just copy that code and put it in my exploit. So that's the way the exploit looks. I connect. I have a NOP sled of 20 bytes. I have the buffer. And then at the bottom, I have this stuff where I create. I make the 181, take away the link to the buffer and the link to the NOP sled. This will pad it to the right place. Then I go to the EIP. This points to my trampoline that does pop, pop, return. So it will now execute that stuff. And that is the attack that works. You can run it in the debugger, and it will now start listening on 4444. And it works outside the debugger because this is not subject to that GDB issue. So that's it. This will start a listening port. This, by the way, is a pretty weak, miserable attack. Anybody with a firewall won't fall for this because their firewall should be blocking traffic on unexpected ports. It would be far more professional to make a reverse shell, which is a minor extension, but this is all I care about for here. And so give it a shot. After you're done with 3, you might want to try 10x or just go down the numbers either way. But it is adding the last couple of wrinkles to move you much closer to exploiting real modern code. Are there any questions?
For no byte, it also applies to the address, any part of the address?
What does?
No byte.
Null byte, yes. Yeah, because what you're putting in is, the question is whether you can have a null byte in an address. And the answer is you cannot, because what I put in was something like a text string. It was the file name for a GET request. So it originally is interpreted as a string. Then later, I reinterpret it as executable code. So the step where it's interpreted as a string causes it to be broken by delimiters, like 0, like 10, like 13. That's the problem. This is the weak spot. Remember, the whole fundamental thing we're doing here is feeding in data that is a string and then reinterpreting the same data as code, which is insane, and that's how it works. This is very much like SQL injection, where you feed in something that's supposed to be a name, but it's reinterpreted as SQL commands. All these attacks rely on the same fundamental misunderstanding. Like you speak a sentence in English, and if you actually speak German, that sentence means something totally different. That's how they're all working. And so you can't have a null or a D or an A anywhere in any of the stuff you put up, not in the address. That's why there's a defense we'll get to called ASCII armored address space that just relocates all the code into addresses that have zeros in them. And that stops this whole category of attacks. Then you can't refer to any of the addresses because they all have zeros in it. You can actually inject 1 0. It has to be the last byte of your attack and it will end the attack. And sometimes that's good enough, but that's very limiting. Any others?
How do they make the address the all zero?
You just adjust the operating system to run in a space that always runs
So
there.
it just jumps?
You relocate it. Modern code relocates all the time. So you can choose to run it in a virtual address. And all code thinks it's running in the same location. It all thinks it's running at 0804. It's a virtual address. You can adjust it to make that virtual address be full of zeros. It's all running like in a virtual machine with the simulated address space. We'll get there. It's one of the defenses. All right, I'm going to stop the share, and I'll go up to the lab and help anybody who wants to work here for another hour or so. And